Now, it's in progress now. I hope you guys are having a good day. It is the 24th. Let's see, the 24th of February. Um, I got a Gmail. Yep. Oh no, oh, okay, that's fine actually. Yeah. Um, so it is the 24th of February. We are, let's see, we've got 2 weeks until spring break, I think. So we got this week, next week, spring break. Um, and with that, we've got, I'm sorry, I'm looking at our schedule right now. Um, we're going to be talking about, let's see, what do we got? What do we got? What do we, that's the wrong class. What am I doing? No, that's the right class. Let's try this again. One more time. There we go. Um, okay, so let's see. What do we have? I can share my screen with you guys. That's the one. 1310, 9:30 a.m., Monday, Wednesday. Today is the 24th, as I said, February 24th. Later today, after our lecture has been recorded and I uploaded to YouTube, I'm going to add the link right here. We've got a total of two activities that are up, activities number 9 and 10. And I kind of made it a little bit more, I guess, direct. Um, so now when you click on activity number 9, it just has your prompt in the description. For this assignment on a separate piece of paper, name two nonmetals that can make a nonpolar bond. Then name two nonpolar that can make a polar bond. And we're going to talk a little bit more about this today, obviously. So I think streamlined it a little bit rather than having you guys have to like download a separate file, open a separate file, and everything like that. So with that in mind, again, not the right class. Why am I doing that? Um, what we are talking about today is we are getting back into our discussion of the periodic table and some elements. Today is the 12th class meeting. We are covering chapters 4.7 to 4.9. We've got the PowerPoint and the PDF. I've also got the PowerPoint and PDF for all of this stuff up through next week. Then, if you look at the schedule, kind of looking ahead, day 16, the Monday after spring break, we're going to be reviewing for our exam, and then our exam is going to be on Wednesday, March 19th. And I know it seems like, man, it really kind of sneaks up on you. Um, yeah, it does. Sneaks up on me too. So, with that ready to go, I just wanted to kind of go through that to give you an idea of what to expect. Now, last time, if you remember what we were talking about, we were going through share. Last time we were talking about a couple of different things. We talked about multiple bonds. We talked about nomenclature. We talked about a couple of different things. Okay. Now with that said, we talked about nomenclature and we used prefixes. Which type of compound? And I'm going to go ahead and add, kind of my options up here. Which type of compound? I'm going to go with a molecular, and I'm going to label that as M, and I for ionic. Add to the chat which type of compound used prefixes. And prefixes like mono, di, tri. Put an M for molecular or an I for ionic. Add that to the chat. And an example would be something like carbon dioxide. And if you want to use my example there, carbon dioxide, I'm going to jump to the next slide and show you the periodic table. So when we have a nonmetal like carbon and a nonmetal come together, what type of compound do they make? Do they make an ionic compound or do they make a molecular compound? Add an M for molecular or an I for ionic. I'm seeing an M. So M, okay. Seems like the responses I'm getting are kind of split there. So if we have carbon dioxide, yeah, covalent slash, I'm going to add that. Thank you that there. So carbon dioxide is an example of a compound where we have carbon, a NM or a nonmetal, and oxygen, which is also an NM, which is also a nonmetal. Okay, so carbon and oxygen are both nonmetals. So these two things come together to make a molecular ionic or an ionic compound. Now, with that in mind, let's go back to this question. Do we use a prefix or do we use prefixes for molecular or ionic compounds? Go ahead and add an M for molecular or covalent or an I for an ionic compound. Okay, now I'm seeing lots of M's. You're absolutely right. So anytime you see a molecular or a covalent compound, you're going to be using a prefix in that name. So carbon dioxide. Because now add to the chat, how many oxygens are present in the compound carbon dioxide? Awesome. Two. Perfect. Great job. Okay. It's been a minute since we talked about that, so I understand. Okay, now what we're going to do is we're going to go deeper into those covalent or molecular compounds. And I want you to be comfortable using these two terms, molecular or covalent, use those two interchangeably. Okay, so here what we have is a periodic table. And this is a good example of a periodic table that I will not be using on your exam. And the reason for that is because, well, what this periodic table is trying to show you is it's trying to give you the atomic number, which add to the chat, our atomic number is the same as our number of protons or neutrons. Protons. Exactly. So our atomic number is on there. Check. The symbol is on there. And, my vision's decent. I can see those two numbers, but then the last number or the last thing that's on here that's really important is this last number. Now, this is a number that if you look at them, if anyone can see this all right, maybe they have the PowerPoint or the PDF open themselves. What is the highest of this small number that's at the bottom of the periodic table in those different cells? What's the largest number? And I'll give you a little bit of a hint. Go in this direction. And it's, you can probably tell that, or many of you are probably looking at your screen saying, it's hard to see that. Yeah, that's exactly why I'm not going to be using this periodic table on your exam. So the highest number, 3.98. Great job, Emma. 3.98, and that is for fluorine. Okay. Now, the lowest number is way over here, francium, Fr, and that has a value of 0.7. Okay, so these numbers range from 0.7 to 3.98. Let's go ahead and just say that it's from 0.7 to approximately 4. Now, that sounds like a GPA range. Like, ooh, I struggled actually, I had a friend my freshman year of college who I think he got a 1.2. 1.1 GPA was his freshman first semester GPA. He got on scholastic probation, but then he bounced back, so he was good. Um, Now, with that in mind, what does this number mean? This number represents something known as electronegativity. Now, electronegativity is measured on a scale from 0.7 to 4. This is also known as the Pauling scale of electronegativity. Okay. Now, the Pauling scale of electronegativity is basically from 0.7 to 4.0. And a good question is, what the heck is electronegativity? Electronegativity is basically a measure of how much does one atom in a bond want electrons. Now, if we have a scale from 0.7 to 4.0, which of these, let's go with francium versus fluorine. Which atom do you think wants electrons more within a bond? Emma, you're absolutely right. Fluorine. So fluorine is what is known as our most electronegative element. Now, do you think that, add to the chat yes or no, do you think that fluorine is more electronegative than arsenic? AS over here. Is fluorine more electronegative than arsenic? Yeah, that's a pretty reasonable thing to say because I just say, hey, fluorine's the most electronegative element. How about that? Now, if we go to the next slide, what we're going to see is what we use these numbers for. So like I said, electronegativity is kind of a measure of how much does one atom want electrons. 4.0 is the highest. This picture right here is more likely what you'll see on your exam. Sorry, this periodic table is more likely what you'll see on your exam because of the fact that, well, those numbers are a little bit more legible. So what we do whenever we're looking at electronegativity is we're able to classify a bond. And we do it by looking at the atoms that are involved in a bond. So if I were to say, let's go with this one right here, hydrogen. What I want to do is I want to take the electronegativity of each of the atoms within the bond and determine the difference. And if I were to do something like this, 2.1 minus 2.1, before we answer that, what do these straight up lines indicate? What do they mean whenever you're writing a math formula or math equation? Absolute value. Absolute value means that you're never going to have a negative number. So let's go ahead and change that up and let's say 3.1 minus 5.0. If I did that, well, I would come up with the negative 1.9. But if I instead write 3.1 minus 5.0, and then I put the absolute value kind of barriers there, what's my answer? It's going to be positive 1.9. Or heck, you could just write 1.9. Okay, can I get a yes or an emoji, something in the chat that, yes, I follow what absolute value is? Okay. Okay, great, 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 great. Okay, so now whenever we're looking at calculating, I'm going to erase all this because I don't need that at the moment. I'm also going to erase the big circle there. I'm going to erase these arrows. Now, with that in mind, what is 2.1 versus minus 2.1. I think I'm going to go with 0. I don't think anyone's going to disagree with that. So what I'm doing is I'm saying which of these atoms, hydrogen or other hydrogen, wants the electrons more, the electrons that are shared between these two atoms? Well, neither of them. They both want those electrons the exact same amount. So what that means is that the electrons, and I'm going to draw the Lewis structure of this, those two electrons are equally shared between these two atoms. Does everyone follow that? Can I get a thumbs up or something in the chat responding that, yeah, I follow? Okay. We're going to work on some more examples, so it might get a little bit trickier. Okay, so when we see something like 2.1 minus 2.1, when we see a molecule where both of the atoms are identical, we can say that neither atom has a greater claim on the electrons. Each atom kind of has, well, each atom can say, yeah, I've got those electrons and I have those electrons. So they're equally being shared. Now, when we go on to look at other molecules, like fluorine and fluorine, what's our electronegativity difference there? Well, we want to take our electronegativity of each of the atoms, 4.0 minus 4.0. We're still going to put an absolute value. What's our difference there? 0. So each of the fluorine atoms here shares those electrons equally. Now, next up, we're looking at carbon and hydrogen. Can anyone add to the chat and tell me what the electronegativity difference is between carbon and hydrogen? Zero 0.4. Now, if anyone is doing this at home and they got a negative value, well, we know that we're not going to get a negative value because we're looking at the absolute value. So you're absolutely right. 0.4 is our difference. We took the 2.4, oh, I'm sorry, the 2.5 up here for carbon, 2.5 minus 2.1. I'm going to put the absolute value markers there, and I'm going to say 0.4. Alternatively, I could have said 2.1 minus 2.5. Again, absolute value, and I get 0.4. So my electronegativity difference between those two atoms is 0.4. Now, with that said, is there one of these atoms that wants the electrons a little bit more? Yeah. But is there, do we really, let me rephrase that. Carbon does want a little bit more. Carbon does want those electrons a little bit more than the hydrogen, but whenever we're looking at those differences, Dolce, you're absolutely right. It's not enough. Okay? So what we're looking for is the electronegativity difference, and we want to see that that difference is less than 5. 0.4 is less than 0.5. So we classify this bond right here, the CH bond, as a non-polar bond. So it's almost like, yeah, they're sharing, but it's not really anything to, be alarmed about. Okay, so now when we look at another classification for a bond, we look at what's known as a polar covalent bond. We're still looking at the electronegativities, But now we're going to see how different they are from one another. Here, what we're looking for is a range from 0.5 to 2.0. If the difference between our atoms is between 0.5 and 2.0, that means that our bond is classified as polar. So polar covalent. Now, what does that mean? Okay, so let's go ahead and put the numbers down. 2.1 minus 4.0. Absolute value, this is 1.9. Okay, so is 1.9 between 0.5 and 2.0? Absolutely. We are going to classify this as a polar covalent bond. Now, next up, nitrogen and hydrogen. Nitrogen is 3.0 minus hydrogen 2.1. I'm going to continue to add those those absolute value markers. 3.0 minus 2.1 is 0.9. Again, between 0.5 and 2.0. Carbon, fluorine. Well, carbon is 2.5 minus 4.0. Absolute value. Well, that is 2.5 minus 4.0 is negative 1.5, but it's an absolute value, so 1.5. So 1.5 is between zero point 0.5 and 2.0. Therefore, this is a polar covalent bond. And then, last but not least, oxygen to hydrogen. Oxygen is 3.5. Hydrogen is 2.1. 3.5 minus 2.1. That is going to be 1.4. Is that between 0.5 and 2.0? Yes, it is. Okay, so what I'm getting at here is basically saying that not all of our covalent bonds are identical. There are some bonds where there is kind of a greater negative balance almost. It's like oxygen and hydrogen, those electrons are being shared between oxygen and hydrogen. These electrons that are denoted by that line, they're being shared, but one of those atoms wants those electrons a little bit more. Now, with that in mind, you can respond with an O or an H. Which of these atoms, oxygen or hydrogen, O or H, wants those electrons more? Add it to the chat, O or H. I got two responses so far. We can get some more. Okay. Okay. Now, I'm seeing everyone put O, and you're absolutely right. And the reason that we know that is because oxygen is our more electronegative element. With the greater electronegativity value, oxygen's almost pulling those electrons. And that term right there, or I always like to use that phrasing, pulling, because that makes me think of, oh, there's a pull, P-O-L-E. There's a pull, P-U-L-L, for those electrons. So oxygen is our more electronegative element, which is why we have this as a polar bond. Okay. Can I get a thumbs up or something in the chat where, yeah, I'm good with non-polar covalent and polar covalent bonds? Okay. Okay, great, great. Now, our last type of bond is one that I always kind of think about it, if we go back to the beginning of this lecture, we talked about molecular covalent or ionic bonds. So we had two major classes. But the way that I think is helpful to think about bonding is to think about it as a part of a spectrum. Um, and I always like to think about nonpolar bonds as being at one end of the spectrum and ionic bonds as being at the opposite end of the spectrum. So I always like to kind of classify ionic bonds as being polar, but they're almost like superpolar. So I'm going to phrase this as superpolar. And what that means is that our electronegativity difference is greater than 2.0. Now, is that what we use to define a ionic bond historically? No. What did we always describe an ionic bond or an ionic compound consisting of? Can somebody add to the chat either what we described an ionic bond consisting of, or an ionic compound consisting of, or add an ionic compound's formula to the chat? Or an ionic compound to the chat. Yeah. I'll give you a hint. If you had eggs, you might have added some of this ionic compound. And I'll give you another hint. It's not black pepper. It's also not cheese or butter. Sodium chloride. Absolutely. So we know NaCl as our ionic compound that we kind of alluded to a couple of times. Now let's check and make sure that that checks out. Na 0.9, Cl 3.0. So 0.9 minus 3.0, we're looking for an electronegativity difference of greater than 2. Not 2, but greater than 2. And that is 2.1. So does this check out? Yeah, it does. Our definition for ionic compound is a metal and a non-metal. Those two things come together, boom, we've got a good definition. But then we can look at the electronegativities and say, oh, well, the electronegativities are different enough that that's another kind of way that we would describe an ionic compound. Okay, now, next up, we've got a poll question, but I'm not going to give this as a poll question. I'm just going to kind of present this to everyone, and we're going to work through this one. Which one of these bonds is most polar? We've got hydrogen-hydrogen, carbon-hydrogen, carbon-fluorine, and carbon-chlorine. What I want to do is just write out the electronegativities of each of these atoms and do monster bars for absolute values. So 2.1 minus 2.1, 0. Carbon, 2.5 minus 2.1, 0.4. Carbon fluorine is 2.5 minus 4.0 equals 1.5. And then carbon chlorine is 2.5 minus 3.0 equals 0.5. Okay, now add to the chat. Boston, perfect. What we're looking for this question is we're just looking for the difference and which one of those differences is the greatest. Now, if we wanted to take this a step further, we could go ahead and rank them. We could say that our most to least, we could say CF is our most polar, then CCl, then CH, and last but not least, HH. And this spectrum gives us from polar to nonpolar, or most polar to least polar. Are these all still classified as polar bonds? Or are they all still classified as covalent bonds? Yes, they are. Okay. Everyone who responded, I saw that you indicated the correct answer, so great job, everyone. Now, another kind of representation or rendering or look at that is this right here. Think about this on the far left-hand side and the far right-hand side as being models of basically the same thing. Now, whenever we look at this one on the left-hand side, we've got this little dagger here. And that dagger has, well, it's got kind of a plus end right here, and then this arrow. Add to the chat, what is the arrow pointing towards? A positive or a negative region of our molecule? Or is it pointing towards where electrons are accumulated or not? What is the arrow pointing towards? Where our electrons have accumulated. You're absolutely right. Great job, Dolce. So if you think, well, what's the charge of our electrons? Electrons are negative. So this is kind of pointing towards the negative end. And then if what's the opposite of negative? Well, it's going to be positive. So within this molecule, we've got a positive region. And I use the terms either region or area. Um, we've got a positive region, we've got a negative region. So our more electronegative element, more electronegative, is found near the, well, more negative region. We've got this model right here. Now, this symbol right here, and then again right here. I've always kind of thought that that looks like a snake. Is it a snake? No, it's not. If I remember correctly, it's the lowercase Greek symbol for sigma, which my I know that I mentioned to you guys that I have kids, and they have iPads, and they're just getting into memes, and they always say, "What the sigma?" I have no clue what that means. Can anyone add to the chat if they have ever heard the phrase "What the sigma"? Okay, there's one yes. I have no clue what that means. Okay, good. There's okay. Yeah, like I said, I have no clue what that means. I'm fine with that. Um, yeah. Okay, thank you very much for adding. Like, what the heck? Okay, good. At any rate, so anytime they mention that, I think to myself, oh, okay, well, we're clearly talking about electronegativities. In this case, what we're looking at is, well, the sigma here represents like partial. So this is a partial negative and partial positive. Okay, so that sigma, that's what that represents. Now, if we look at this model on the far right here, what color do you think is indicated by kind of a reddish pigment? Is that reddish pigment where it's more negative or more positive? Is my question. Sorry, I should have. My phrasing was a bit funky there. I apologize. Exactly, it's more negative. So when you look at this, this is what is known as an electron density map. And you sometimes might hear it referred to as an electron density model. So whenever you look at this, well, we have a greater kind of abundance of electrons here, which is indicated by the larger shape, but also the color. It's a little bit more red and it's a little bit larger on the right-hand side of our molecule. And that's basically our fluorine, and this is our hydrogen. So our electron density map shows, well, where are the electrons more commonly found? They're more commonly found on this side of the molecule. So there's a couple of different ways that I want you to be able to look at a bond. I want you to be able to, one, calculate E negativity difference. Do I need you to memorize the electronegativity values? No, not at all. I will always provide you with the necessary electronegativity values. I want you to be able to classify bonds as nonpolar, polar covalent, and ionic. So three classifications. And when it comes to that, basically these numbers. Is it less than 0.5? Then it's nonpolar. Is it between 0.5 and 2.0? Then it's polar. Is it greater than 2? Then it's ionic. I want you to know those three ranges. I mean, arguably, you could say, I need to know one range, 0.5 to 2. Anything below that is nonpolar. Anything above that is ionic. So I want you to know those. I will always give you the electronegativity values so you can calculate that difference. And then based on that difference, you can classify. Then I want you to be able to apply those numbers and look at and identify which is my more electronegative element. And once you have that, then you can say, all right, well, based on this being more electronegative, sorry, my cadence was a little bit funky there. Based on that, well, then I'm going to draw this, this dagger, and it's going to point this way, or it's going to point that way, or it's going to point this way. Or I know where to put my partial positive or partial negative. So as an example, let's go ahead and look at this. C to H. We did a calculation of that. And now what I want to do with this is come back and say, all right, well, carbon to hydrogen, how did we classify that bond? Well, we have an electronegativity difference of 0.4. Okay, so how do we classify that bond? Is it polar? Is it nonpolar? Or is it ionic? Add it to the chat. It's less than 0.5. Nonpolar. Great job, everyone. Okay, so that's a nonpolar bond. So if you're thinking about this in terms of like, well, what might I see on an exam? One of those questions might be, well, classify the bond. Okay, so you guys all answered that. So that's a question that you would see on an exam. You'd classify that bond. Another way that you might see this sort of thing on an exam is like this. Um, Bear with me for a second. Which one of these models effectively or correctly shows where the charges are? Basically, where the assigns the partial negative to the more electronegative element correctly. Is it A or B? Add that to the chat. And as your model, before you answer it, you can look at this one up here. Which is our most electronegative element? This one right here. So use that as kind of your guide. Is it A or is it B? Carbon has an electronegativity of 2.5, and hydrogen is 2.1. And I understand it probably seems like I just lied to you because I was like, I will always give you the electronegativity values. And then I promptly ask you a question and I don't give you the electronegativity values. Okay, so and fluorine is 4.0, hydrogen is still 2.1. So our more electronegative element gets that sigma negative. So our correct answer is going to be A. So I apologize for not giving you those pieces of information that you need to be able to answer this question. Okay, so there's a couple of different ways that you can see this. Classify the bonds, apply daggers. Sounds like you're getting a skill set of fighting or something like that. Apply daggers, that's a G. Then apply sigmas. And then last but not least would be correct density map. And if you're looking at that and thinking, well, how do I know which is the density map that's correct or incorrect? Well, I would give you a structure like this, and I would say our molecule is HF. And then I would say, okay, well, HF. Is this drawn correctly? Or are the atoms labeled correctly? And you'd look at that and you'd be like, okay, I know that the larger area, the larger sphere, is by my more electronegative element. Between hydrogen and fluorine, well, I know that fluorine has an electronegativity of 4.0 and hydrogen is 2.1. So is this are these labels on the correct atoms? No, they're not. So that's why that would be an incorrect model. Okay. So what I've got here in the lower left-hand corner are basically like five sorts of questions that you could kind of anticipate and ones that you should be able to answer. Calculate the electronegativity difference, classify bonds, apply daggers, apply the sigmas, and which is the correct electron density map. And if you're thinking, ooh, is that all? That's pretty much it. And I know that that kind of simplifies it, but I feel like these questions are kind of a progression where I ask you about, well, what's the electronegativity difference? Well, in order to calculate that, I'm going to give you a chart that looks a little bit like this. So you'll be able to calculate that based on here's the two atoms that are in the bond. And then after that, the classification, what you guys need to remember about the classification is what are the possible ranges? Okay, can I get a thumbs up or a response in the chat if you're good with these responses or good with these kind of potential questions and you understand like, okay, I could kind of formulate some of my own. Okay. Okay, great. All right. So what we've been talking about here is we've been focused on individual bonds. We have not been talking about, well, these within the molecule. Is the bigger side of the density map, is that the negative? Great question. The larger side, let me erase this just so I can avoid any sort of confusion there. I'm going to kind of update this. The larger side, you can kind of think about it as larger side is where more electrons are. Thank you for asking that question, Melanie. So that's what we're looking at there. The larger side is where more electrons are. And so as a result of that, the this is the negative side. Oh, Dolce, fantastic. Great question. Absolutely. Okay. If it's cool with you, I'm going to just jump back here and I'll use all of these as examples. So, I'll add, okay. So CF, then we'll go to CCl, and I'll just start off there. So whenever I look at carbon fluorine, I'm going to be drawing this arrow. And what I want to know is the plus side, or where do I place the plus side and where do I place the arrow? The arrow is going to be pointing towards the more electronegative element. Arrow points at more electronegative element. So then what I'm going to do is I'm going to look at carbon with a 2.5 and fluorine with a 4.0. So 2.5, 4.0. I always kind of think about this as where are the electrons more likely to be? The electrons are more likely to be by that electronegative element. So I'm going to have, that's my, I've got that right there. Now for carbon chlorine, well, 2.5 and 3.0. Carbon is still less electronegative, so I'm going to draw it like that. Now, how would I classify CCl? I'd classify that as it's a polar covalent bond. Now, let's look at CH. C is 2.5, hydrogen is 2.1. Okay, here, sorry, I jumped onto the other side of the slide, the upper right-hand corner. Well, which one is more electronegative between carbon and hydrogen? Is going to be carbon. So I'm drawing my arrow going towards carbon. And then last but not least, H, H. I don't really have an arrow to draw because they're equally electronegative. So if I were to draw an arrow, they would basically cancel one another out. So I'm not going to draw an arrow. So even though this one that I'm putting a box around, how would I classify that? I would classify that as NP or non-polar covalent, but I'm still going to be able to draw that dagger because I'm going towards my more electronegative element. Does that make sense? Absolutely. Great question. Thank you very much for asking. Now, if I wanted to draw kind of a, let's go with, I'm going to erase some of my writing here. If I wanted to draw something like a electron density map for, let's say, CF, what I would do is the smaller side corresponds to the more positive side. So I like to draw those dagger models and then come up with something that looks like this. And that's not a fantastic drawing, but the larger side is by my more my more negative and more electronegative element. So that's what that would look like. Whereas CH would look a little bit more like this. Where and the magnitude of those and the size of the kind of more spherical side, that's just because I'm looking to improve as an artist. Okay, so these are five good questions that you could have and be able to answer based on all of this. What we're talking about here is just bonds. Now, when we talk about bonds, we also want to be able to apply those to a molecule. And so what we've got is we're looking at this in the context of individual molecules. Now, with that in mind, let me just pause for a second. Um, what we want to be able to do is look at each one of these kind of bonds and classify it and draw the daggers. So today, and this is where we're going to end today, and I know it's a little bit earlier, but I just want to do this kind of very deliberately so everyone kind of is good on it. If we were to draw something like oxygen and water, okay, O or H, which is more electronegative? Oxygen or hydrogen? Oxygen, absolutely. So now, if we were to draw water, I'm going to give you two examples, and you tell me which one is right. A and B. Or which one of those daggers is correct? A or B? Okay. Okay. So if you wanted to draw water, really kind of look a little bit more like this. So then if we were to draw water and, oh, what's that lone pair of electrons? That's another lone pair of electrons. Man, oxygen's got a lot of electrons around it. And I know that I kind of mentioned this previously, but a lone pair of electrons versus a shared pair of electrons. I'm going to draw a box around a shared pair, circle around the lone pair. That box right there, um, those two electrons are actually here. You know what I'm going to do is I'm going to say A or B. Which pair of electrons, A or B, is kind of more contained, more limited on where they can go? A, you are absolutely correct. A are more contained because, well, those electrons here are either going to go towards oxygen or hydrogen. Now they're going to gravitate more towards oxygen because oxygen's more electronegative, but these electrons up here, the lone pair of electrons, they really kind of have this sort of free reign. They can fly all over the place. And what that means is that this structure right here is really a good model for what water looks like because of the fact that these oxygens and hydrogens, or sorry, the electrons that are around that oxygen, that's kind of where they're going. I just got a private message about poll questions, and I'm going to assess poll, I guess, answers based on attendance. And so I can pull your attendance up just on Canvas or a Zoom report. But that's really where I wanted to stop today. Um, this is dense stuff. If you're thinking, how can I study for my next exam? Be able to answer these questions. I would recommend that you can come up with questions based on these yourself. And that would be a really good practice. So, just kind of pick two elements using this chart right here. Say, what's the electronegativity difference between Mg and Cl? Are we talking about bonding or anything like that? Are we talking about making a compound? No. I just want to know what the electronegativity difference is there. Oh, it's 1.8. Okay, cool. How would I classify that bond? Okay. Well, I'm going to stop my share right there. Then I'm going to say, I hope you guys have a great afternoon. I hope you have a great rest of the day. I will be back with you guys on Wednesday. I've got office hours today at 12:30. I'm going to stop my recording.